today in section 4.5, it's kind of broken down into two parts. So part of section 4.5 talks all about how confidence intervals and hypothesis tests are related and when we should do which one in a particular scenario. And going along with that, also looking at the similarities and differences of sampling distributions versus bootstrap distributions versus randomization distributions. That's really, that whole part is really what I want you to get out of section 4.5 and what I'm going to be testing you on. So there's kind of three main things then from section 4.5 that I'm going to test you on. Okay, first, I want you to be able to use a confidence interval to do a hypothesis test. Okay, second, I want you to be able to read the research question and know whether a hypothesis test or a confidence interval would be most appropriate to answer that question. And then third, I want you to understand the similarities and differences between sampling distributions, bootstrap distributions, and randomization distributions. The other part of section 4.5, if you read it in the textbook, it talks all about how to create randomization distributions and the different methods that can be used to actually come up with these randomization distributions. Because we talked about it briefly when we introduced randomization distributions. We talked about one way of saying, okay, if the null hypothesis was true, then here's how we could simulate taking samples in that scenario. But depending on if you're looking at, correlation or one mean or one proportion, two proportions, and even depending on if your data was an observational study versus an experiment, there's different methods that we use to be able to simulate taking samples under the scenario of the null hypothesis being true. And I actually find section 4.5 to be like super fascinating because it explains kind of the why and where does everything come from and how does it work kind of thing. But I'm not going to test you on that part. So if you don't care, you don't have to read that part. But if you're interested, then it's a good read just to read through it and be like, oh, okay, that makes sense. And now I get it. Now I understand where they got this randomization distribution from. So the notes pages over this section, I didn't actually write out notes because I already told you there's only those three main things that I want you to get from this. And going along with those things, I actually thought having examples in your notes would be better than having, you write out a few sentences for each thing. So in lieu of kind of notes, what I gave you in place of notes was a printout of all the slides. Because then you'll have all these examples handy. And when you go back to look at it, you can be like, okay, yeah, that's why we chose that, and here's another example. So that was a long explanation for what today is. So first of all, let's talk about confidence intervals and how we can actually use a confidence interval to do a hypothesis test. And if you remember, a confidence interval is this range of values where we're pretty sure the population parameter is. In fact, we said that all the plausible values for the parameter are inside this interval, and if there's a value that's outside that interval, we're saying not a plausible value. So thinking about that then, if we have a set of hypotheses and we're saying null hypothesis equals 5, for example, let's say mu equals 5 in the null hypothesis, and we're able to construct a confidence interval and 5 is not in the confidence interval, then 5 would not be a plausible value and we'd be able to reject the null hypothesis because we would have evidence that mu was not equal to 5 based on our confidence interval. And similarly, if 5 was in our confidence interval, then it would be a plausible value. Therefore, we would not have evidence that the null hypothesis was false. And so we would fail to reject it. So essentially, we can use our confidence interval along with our hypotheses to make a fail to reject type of decision on our hypothesis test. And so this says if a 95% confidence interval contains the parameter given in the null hypothesis, then in a two-tailed test, we would not reject the null hypothesis at the 5% significance level. And if a 95% confidence interval misses the parameter, then a two-tailed test would reject the null hypothesis at the 5% significance level. So let's talk about kind of the relationship between confidence level and significance level when we're using a confidence interval to do a hypothesis test. So there's basically they go hand in hand. So if I am basing my conclusion in the hypothesis test using a 95% confidence interval, then if I take 1 minus 95, that means my significance level is 5%. So if I'm using a 99% confidence interval, that would mean that my conclusion would be valid at the 1% level, because 1 minus 0.99 is 0.01 or 1%. If I'm using a 90% confidence interval, that would mean that my conclusion is valid at the 0.10 significance level, because 1 minus 0.9 equals 0.10. Does that make sense? So if I want to know what's the significance level that this test and this decision in this test, rejecting or failed to reject, is based on, I just take 1 minus the confidence level, and that gives me the significance level for my test. Okay, so here's kind of a little example. Let's say that using bootstrapping, we found a 95% confidence interval for the mean body temperature for healthy adults to be between 98.05 and 98.47. Now, thinking about your life, like my whole life, I've always heard that the body temperature, like the normal body temperature, like what's your whole life? What have you always heard? Oh, normal body temperature is this. Maybe it's just my whole life because I'm old, but maybe some of the other old people out there can tell me what they've heard their whole life. All right, thank you, other people. And not even all of you are old, so none of you are old. I'm older than all of you, so all is well. So yes, 98.6. Okay, so 98.6, like you always hear, hey, that's the normal body temperature if you're just healthy, you're a healthy adult. So now we've collected some data from a bunch of healthy adults, and we get a confidence interval that goes from 98.05 to 98.47. So if I think about the hypotheses, trying to see if, hey, is that really the mean body temperature for all healthy adults? My null hypothesis would be mu equals 98.6. My alternative, mu not equal to 98.6. Is 98.6 in that interval, in that confidence interval that we created? Is it one of the plausible values based on our confidence interval? And no, it's not in the interval, right? 98.6 is not in the interval from 98.05 to 98.47. So because 98.6 is not in that interval, we would actually reject the idea that the mean body temperature for all healthy adults is equal to 98.6, and we would conclude it's something different than that. So that's kind of the basic way we're going to use this. So I have a few more examples, and I think this will start to kind of sink in. So here's a question that they asked adults aged 18 to 29 in 2010. They asked them, does a child need both a father and a mother to grow up happily? And in 2010, based on their sample, they got a 95% confidence interval for the people who would say yes to that, went from 0.487 to 0.573. So let's say we're testing null hypothesis P equals 0.5 versus the alternative P not equal to 0.5. Basically, we're like looking to see if a majority of people, of adults, would say that a child needs both a father and a mother. So based on this interval and these hypotheses, what should be our conclusion? So A, should we reject the null hypothesis? B, should we not reject the null hypothesis? C, should we reject the alternative hypothesis? Or D, should we not reject the alternative hypothesis? All right, good job. I'm seeing lots of B's over there in the chat window, and that is the correct answer. So to use the confidence interval to do the hypothesis test, all I have to do is look and say, okay, here's the value under the null, 0.5. Is 0.5 in that interval? If the answer is yes, we don't reject. If the answer is no, we reject. So it's just It's really just that basic. And I threw these extra answers on here just to try to trip people up about the alternative, but I wasn't able to trick anybody. So we don't reject or fail to reject the alternative. We only reject or fail to reject the null. So those are just bogus answers. So since 0.5 is in the confidence interval, it's a plausible value, so we would fail to reject. Okay, in 1997, they asked same question to adults age 18 to 29, and this time their confidence interval in 1997 went from 0.533 to 0.607. So what should be our conclusion in this test if we're using that confidence interval to do a test? Yeah, so this time 0.5, not in the interval. So it's not a plausible value, which means we can reject the null hypothesis because the null hypothesis, not plausible. Good, okay. Now suppose we're testing null hypothesis mu1 equals mu2 versus the alternative mu1 not equal to mu2. And we get a 95% confidence interval for the difference in the two population means. And that interval goes from 0.12 to 0.54. What should we conclude about this test? Okay, so everybody's putting A, which is correct. We're going to reject. And in the case of anytime we're comparing two means or two proportions, the value that we're looking for in the interval is 0, because if the null hypothesis was true and mu1 was equal to mu2, then mu1 minus mu2 would be 0. If they're the same, you subtract them, you get 0. So anytime we're comparing two means or two proportions, we're looking to see if 0 is in that interval. And right now 0 is not in the interval. So if the value is not in the interval, we reject. Okay, what significance level would we be using for this test? If we use this confidence interval to do this hypothesis test, what would be our significance level? All right, good. So remember that if we're doing a 95% confidence interval, we can figure out the significance level. Remember, significance level is alpha, just by taking 1 minus the confidence level. So 1 minus 0.95 is 0.05. So our significance level, alpha, would be 0.05. All right, now let's say we're still comparing two means here. Now we have a 90% confidence interval for the difference, and it goes from negative 2.1 to 5.4. Should I reject or fail to reject if I'm doing a hypothesis test with this confidence interval? Yep, this time, again, we're still looking for 0 in that interval. 0 is in the interval this time. So that means that it is a plausible value, meaning that the null hypothesis is still plausible. So we're going to fail to reject. And another way to look for 0 in the interval is look at the signs on your upper and lower bounds. If the signs are the same, then 0 is not in the interval. And if the signs are different, then 0 is in the interval. Okay, and what significance level would we be using for this test? Right, we're going to take 1 minus 0.90, so we'd be using a significance level of 0.10. All right, next one, still testing mu1 equals mu2 versus mu1 not equal to mu2. This time we get a 99% confidence interval, and it goes from negative 10.8 to negative 3.7. Should I reject, fail to reject? This time I should reject because 0 is not in the interval. The signs are the same. So the null hypothesis is not plausible. And what's the significance level that we're using for this one? Right, this was a 99% confidence interval. So 1 minus 0.99 is 0.01. All right, so that's how we're going to use a confidence interval to do a hypothesis test. Okay, we're just going to look at the hypothesized value, see if it's in the interval, and we can draw conclusions based on that. So you might be thinking, okay, if I can use a confidence interval to do a hypothesis test, then why did she make me learn all this stuff about randomization distributions and counting dots and finding p-values? Like, that was so not fun. That was so much work. And all along, I could have just been using this confidence interval that now I'm a pro at, because that was way back in chapter 3. And basically, although we can use a confidence interval to do a hypothesis test, when we use the confidence interval, then it allows us to make a reject, fail to reject type of decision but it doesn't give us any idea of the strength of our evidence. So one thing we gain by doing the whole randomization distribution and finding the p-value and all that good stuff is that we have a measure of how strong the evidence is against the null hypothesis. So if I know that my p-value is 0.0001, for example, this not only tells us that we should reject the null hypothesis, but it also tells us that we have really strong evidence against the null hypothesis. So just using a confidence interval for the test just says, oh, my significance level is this, I rejected it at this level, but it doesn't give me any idea of the strength of the evidence. And we couldn't live without confidence intervals either, because in a hypothesis test, we get this measure of how strong the evidence is against the null hypothesis, but we don't get an estimate of how big the difference is. So hypothesis testing tells us that there is a difference, but a confidence interval answers the question of how big is the difference. So confidence intervals and hypothesis tests, like they both play a part. So we can't just go with one or the other. We really need to have both of them. And the one that we want to do is going to depend on what your purpose is. Like, what's your goal for doing this study? What are you trying to find out? So we're going to look at a couple of examples, and I'm going to give you some tips on how to decide. And then I actually made a Kahoot with more examples for you guys to try out. So I'm not going to go through all the examples that I have in the slides, but you'll have the slides so you can go back and practice those. So I made new examples for my Kahoot so that nobody would have an unfair advantage. But I do want to go through the first few here so we can get an idea of how do you determine which one's better. So, so here's my research question. On average, how much more do adults who played sports in high school exercise than adults who did not play sports in high school? And so we want to decide, should I use a confidence interval to answer this question? Should I use a hypothesis test to answer this question? Or is statistical inference not even relevant for this question? So let's think about each of these things. First of all, confidence interval. Okay, so the purpose of a confidence interval is to estimate the value of a parameter. So we want to do a confidence interval when we want to know, like, we want to have a quantity. We want to know, like, how much more, or what is, or, you know, give me a value here. A hypothesis test is to assess the evidence for claim about the population. So in a hypothesis test, we want to know, like, you know, is this better? Does this have more, whatever, something like that. And then if statistical inference is not relevant, remember what statistical inference is. So statistical inference is using sample data to draw conclusions about the whole population. So an instance where it would not be relevant to do statistical inference is if you didn't have sample data, but you actually had the population. Or if it was easy to measure everybody in the population, then you don't need to do statistics because you can have the actual answer from the population. So instead of using a sample to guess what the population value is, you could just measure the population, have the real value, and be done with it. Okay, so those are going to be our three options on these questions. So thinking about this one here, what do you think is the appropriate way to answer this question? Confidence interval, hypothesis test, or do you think statistical inference is not relevant here? All right, so this one is confidence interval because we want to know how much more do adults who played sports in high school exercise than adults who did not play sports in high school. So we're trying to quantify something. Next question here. Do a majority of adults take a multivitamin each day? What do you think about this one? Confidence interval, hypothesis test, or do you think inference is not relevant? All right, this one's a hypothesis test. So another way that you can look at these questions is by the type of answer that you would give to the question. So if you were to ask the question and the answer to the question would be a number, then you would choose confidence interval. And if you ask the question and the answer to the question is a word, then you would use a hypothesis test. So looking at the ones we've just done so far, do a majority of adults take a multivitamin each day? The answer to that would be yes or no. So that has a word answer. So hypothesis test would be the right choice. Looking back at the one we just looked at, the first one says, on average, how much more do adults who played sports in high school exercise than adults who did not play sports in high school? So that's going to be a number answer. It's going to be like 5 hours a week or something like that. So because it has a number answer, then we would answer that using a confidence interval. And here's another one. Who is older on average, the Final Five or the Fierce Five, which was the 2016 or the 2012 USA Olympic gymnastics teams? So what do you think? Confidence interval, hypothesis test, or statistical inference is not relevant? All right, yeah, on this one, inference is not relevant because we're looking at 5 people, the Final Five and the Fierce Five. If I got on the internet, I could probably easily figure out the ages of the Final Five and the Fierce Five, and then I would know who was older on average. I wouldn't be wanting to take a sample of some of the 5 and another sample of the Fierce Five, because that would be ridiculous, because I could just easily find the answer to all of them just by Googling it. So if the population data is easy to obtain, then we don't need to do statistical inference. Okay, does anybody have any questions on that, how that's going to work? Because now I'm going to put you to the test and test your knowledge with my fabulous Kahoot that I created. All right, good job. So do red cars get pulled over for speeding more than black cars? That would have a word answer, so it's going to be a hypothesis test. All right, good job. Almost everybody got this one too. So what is the mean time to wait in line to early vote? That will be a confidence interval because that would have a numerical answer. Ooh, little trickier one here. So we want to know how much more do college graduates earn than non-college graduates? So how much more, like the answer is going to be like $30,000 a year or something like that. So it's going to have a number answer. We're trying to quantify something, how much. So that's what's going to make it a confidence interval. All right, a little bit of movement in the top. Ooh, it's a tricky one. What percent of American Idol seasons had a female winner? So there haven't been that many American Idol seasons. I'm pretty sure we could just go on Google and find out the answer really easily. We wouldn't need to take a sample of the seasons because there's only been, I don't know, when did it start? Even if there's been 30 seasons, which I don't think there's been that many, then we could easily go find the answers online. So statistical inference would not be appropriate. Ooh, we're kind of split on this one. All right, so is it cheaper on average to buy textbooks from Amazon or Barnes and Noble? So the answer to that question would be Amazon, or it would be Barnes and Noble, right? So is it cheaper to buy textbooks from Amazon or Barnes and Noble? So that one has a word answer, so we're going to use a hypothesis test. It would be a confidence interval if we said something like, how much cheaper is it to buy textbooks from Amazon? Oh no, not very many people chose the right answer. So this one in our class, do the males or females have more Facebook friends on average? So in this case, like we only have like, there's only 26 people here today, 27 including me. So all we would have to do is just say, hey, everybody type how many friends you have in the chat window and, you know, type whether you're male or female. And I think we could easily figure out who has more. So we wouldn't need to take a sample of our class in order to figure this out. We could just look at the whole population. So that's why statistical inference would not be appropriate. A few more questions, see if anybody can take over the top. Ooh, nice job. Okay, so this is going to be confidence interval. On average, how many credit hours per semester do college students take? The answer to that would be a number. Good job again. Okay, so do a majority of households in America own a pet? So your answer would be yes or no. So that's a word answer. So we're going to do a hypothesis test. Oh, good job again. So what is the difference in the proportion of male and female students who major in statistics? We're trying to quantify that difference. So we're going to use a confidence interval. This is the last question, last chance. All right, good job. Okay, so do Texans prefer Bluebell or Creamy Creations ice cream? So the answer to that would be Bluebell. Pretty sure that's the right answer anyway. Just kidding. Yeah, maybe we have some diehard Creamy Creations fans out there. So in other words, it would be a word answer, and so we would use a hypothesis test. So let's see how our leaderboard ended. Third place, Yasmin, woohoo! Second place, Jean, nice. And winner with the fastest fingers in the class, Kaylin. So runners up, Ingrid and Olivia. So good job, guys. That was fun. Okay, so now I just want to talk about sampling distributions, bootstrap distributions, and randomization distributions. And we want to look at the similarities and differences between all of these, because you've been using all of them now. And when you think of all these things, you probably just think of like pushing that generate 1,000 button, that 1,000 samples button like a million times. But how are they similar? How are they different? When are we going to use which one, kind of thing? So starting with sampling distributions. Sampling distributions is what we started talking about at the beginning of chapter 3. And who remembers what the shape of a sampling distribution is? Right, bell-shaped symmetric, right? If our sample size is large enough, then the sampling distribution will be bell-shaped symmetric. And I don't have these coming on one by one, so I'll just put the whole thing up there in case you're writing it down. The center of our sampling distribution is going to be the same as the population parameter. And that's because, remember, in a sampling distribution, what we're doing is we're taking lots and lots of actual samples from the actual population. And then from each of those samples, we're calculating our sample statistic. And then we're doing a graph of all those sample statistics. So one dot on a sampling distribution equals one sample statistic, one real sample statistic, because this one came from a real sample from the real population. Now let's think about bootstrap distributions. Oh, well, first I should mention, when we talk about sampling distributions, the spread of the sampling distribution, we call that the standard error. So that's basically just the standard deviation of the sampling distribution, but we give it that special name of standard error. Bootstrap distributions are used for confidence intervals. And to create a bootstrap distribution, what we're going to do is we're going to take one sample, and we're going to use our one sample, and we're going to sample with replacement from that original sample to come up with a bunch of bootstrap samples. From each of those bootstrap samples, we're going to calculate our sample statistic, which we're going to call our bootstrap statistic because it came from a bootstrap sample rather than a regular sample. And then the distribution of all those bootstrap statistic values is our bootstrap distribution. So thinking about the characteristics of the bootstrap distribution, the shape of the bootstrap distribution is also going to be bell-shaped symmetric if your sample size is large. The center of the bootstrap distribution is going to be equal to the original sample statistic. So that's because we're sampling from our original samples. So the mean of all those bootstrap statistics is going to be equal to our original sample statistic. So that's different from the sampling distribution. The spread is going to be similar to the standard error of the sampling distribution. And if I think about what one dot equals, and really what I'm trying to get at with like what is one dot is to try to help you understand like where these numbers are coming from. So one dot equals one bootstrap statistic. So it came from a bootstrap sample, not a real sample. So that's another difference between sampling distribution and bootstrap distribution. All right, now let's look at randomization distribution. So we use a randomization distribution to do a hypothesis test. And the shape of the randomization distribution is the same as the other two. So it's going to be bell-shaped symmetric if n is large. But let's think about how we construct a randomization distribution. So a randomization distribution is we're going to simulate taking samples, assuming that the null hypothesis is true. And that's really the key to a randomization distribution is we are going to force the null hypothesis to be true. And then we're going to simulate taking samples with the null hypothesis being true. So if the null hypothesis is forced to be true, then the center of our randomization distribution is going to be the value of the parameter if the null hypothesis is true. And then the spread is going to be very similar to the standard error from the sampling distribution. And one dot on our randomization distribution equals one of these simulated sample statistics. So just like the bootstrap distribution, then it's not a real sample statistic. It came from a simulated sample. And the main difference between the bootstrap distribution and the randomization distribution is that for the randomization distribution, we're forcing the null hypothesis to be true. And this is where if you read in section 4.5, then you can find out, well, how do we do that? Like, how do we force the null hypothesis to be true and then simulate taking samples from that? And there's lots of different ways. There's even multiple ways. You know, if you're doing a test of one mean, there's a couple of different ways you can do it just within the same test. So I do recommend reading 4.5, even though I'm not going to ask you specific questions about that. Okay, so looking at these three distributions here, you can see that the main differences between them are, first of all, the centers are all very different. And then what one dot equals, which is going along with like how it's constructed. So it's really important that you understand that you understand the differences in the centers for these three distributions, and that you understand how each of these different distributions would be created. And then really the goal of all these distributions, or at least the bootstrap and the randomization distribution, is to estimate that standard error so that we can draw conclusions. We can do statistical inference. Okay, so I have a couple more questions for you to see how well you understood all those comparisons that we just talked about. Okay, so here's my question. Let mu be the average amount of sleep college students get per night. And it says that data was collected on a sample of students, and for the sample, X bar was 6.7 hours. So it says a bootstrap distribution is generated to create a confidence interval for mu, and a randomization distribution is generated to see if the data provide evidence that mu is greater than 7. So I'm going to do a poll rather than the window this time, so your answers can be all anonymous. Okay, so there's two distributions given down here, A and B. which one do you think is the bootstrap distribution? All right, I think most of you have voted now. Still about 5 people that haven't voted. So here's the results. It looks like most people chose B. That's actually incorrect. So the correct answer was A. So how do we know that A is the bootstrap distribution? Well, if I look back at my chart, see if I can get up there, then I can see, whoops, I went too far back up to my chart. There we go. If I look back at my chart, I can see that the bootstrap distribution is centered on the original sample statistic, and the randomization distribution is centered on the value of the parameter if the null hypothesis is true. So going back to my example here, there we go. Then it tells me that my original sample statistic is 6.7. So A is the distribution here that is centered at 6.7. So I know that one is my bootstrap distribution. If I look over here, it says we could do a hypothesis test, and our hypothesis test would be looking for evidence that mu is greater than 7. That means that the null hypothesis would be that mu equals 7. And you can see that distribution B here is centered on the value under the null hypothesis. So B would be the randomization distribution. Okay, let's look at the next one here. I can make the slide go on. Here we go. Intro stat students are surveyed. We find that 152 out of 218 are female. Let P be the proportion of intro stat students at that university who are female. A bootstrap distribution is generated for a confidence interval for P, and a randomization distribution is generated to see if the data provide evidence that P is greater than 1/2. So which of these distributions, A or B, is the randomization distribution? Okay, perfect. Okay, so here we go. This time, most people put A, and A is the correct choice this time. So we said that the bootstrap distribution is centered on the sample statistic, and the randomization distribution is centered on the null hypothesis value. So we're looking for the randomization distribution this time, and it said that we want to see if the data provide evidence that P is greater than 1/2, which means that my null hypothesis would be that P equals 1/2 or 50%, 0.50. So A is the distribution that is centered on 0.5, the null hypothesis value. And then the bootstrap distribution would be centered on my sample statistic value. And if I take 152 divided by 218, I get 0.697, or essentially 0.7. So you can see that B is centered on my sample statistic value. So B would be my bootstrap distribution.